Log on, tune in, find out. Another good idea from Cambridge.
Do the last talk in the sessions by Thomas Carraro.
Thank you for the introduction. I don't know, does it work? So I have mine. Sorry about that. I thank, in any case, the organizer of this of the series of the DAE and the organizer of this special event, Tadeusz Suczyński and Andrew. And okay, I present my there are two main topics, main contribution from my talk. One is presenting a numerical method in the framework for OED, optimal experimental design, the framework of partial differential equation, and the other one is to give a new perspective of optimal experimental design in the context of partial differential equations. So the goal is to derive in a rigorous way in this framework using the notation of the community of optimization with partial differential equation is to derive a setting for optimal experimental design. And this I do consider the optimal experimental design as a link between the mathematical problems, which are in my case differential equation, especially PDE. OED is a link to the experiments, of course, as we have seen in several contributions here. But I consider this as an optimization tool which has its aim to optimize the sensitivity of an optimal point. So I consider the parameter estimation as a parametric optimization problem, and OED try to optimize the optimal point of this parametric optimization. Of course, to link the model to the experiments, we need a statistic, and I try actually to add this part as further as possible, try to derive everything in a deterministic way, and then and then find a link with the statistic. So first of all, we need some notation. So my model is the A of U is a state in an Hilbert space, Q are parameters that I am going to estimate, and I consider P perturbation of parameters. So perturbation parameters. P are perturbation of the data in this case. Z is an observation space, and I define C an observation operator, which can be a point measurement, a line measurement, or whatever. And I consider a model for the errors, which is a function of true value of the data perturbed by a perturbation parameter. So the parameter estimation problem, capital lambda, is defined this way. I define a solution operator, which is a map from the parameter Q to the state U. I define a map parameter to output, which is a combination of the solution operator with my observation operator. So I go from the parameter space to the space of the data, and my parameter estimation problem, capital lambda, is a map from the data Z to Q hat, which is the optimal point of the parameter of the optimization, let's say the least square solution. Then I consider the perturbed parameter estimation problem. So capital lambda is now parameterized by a parameter P, which is a perturbation of the data, and I say that capital lambda is a map between perturbed data to an optimal point, which is a function of the perturbation of the data. So if P is a random variable, P0 is the realization of this. P0 are the data, is the data that I'm using to solve the least square problem. So gamma at the point P0, after having collected the data, it's a map from the data collected to the actual fit. So the parameter estimation problem, it's an optimization problem, so it's minimization of a functional of the state of the parameter that I want to estimate, and the perturbed setting, it's considering here in the objective function, which is a least square, a perturbation of the data. The state is dependent on the equations, it depends on the state and parameters, and actually you can consider here also a perturbation of the model, but I'm not doing this here. Of course, in the framework of PDE, I consider the model now in a variational form. So I consider a test function, and I give this, and I use this notation. And the reason is that I'm going to solve the PDE by the finite element model, the finite element method, and the variational formulation is the more natural way for using a Galerkin approximation. So as an example of this perturbed parameter estimation, it's a least square where I have the data, and where I have the model. The data are perturbed by the perturbation parameter, and I consider as PDE diffusion, transport, and reaction. So the error model can be additive, can be a relative error, can be whatever function of the perturbation. I consider now the reduced formulation because it's easier for me now to set everything for OED. So I define the least square, the functional j, as j hat, where I put instead of the state, I put the solution operator. That means j is now only a function of q and the perturbation parameter p. If q hat is a local solution of reduced problem, then it satisfies the first order optimality condition, which is an inequality in case of constraint optimization, and it is this equality, the gradient has to be 0 at the optimal point in the case of unconstrained problem. So normally we consider in OED only the unconstrained problem for the parameters, because it doesn't make sense actually to have active constraint on the parameter from the physical point of view mostly. So if there are active set for the parameter, there is something wrong. The model is wrong or the data are too in any case, we can consider also this formulation and go on, and then you define the confidence range are not more symmetric, of course, because you have constraint on the parameters. Now we consider sensitivity of the optimal point. So this is the optimal experimental design. Is consider the sensitivity of the optimal point. So consider how much the optimal point is sensitive to a perturbation of the data, and try to optimize the sensitivity of the optimal point. So the sensitivity of the optimal parameter q hat is given by this equation, which is the second derivative with respect to q of the functional, or this functional. It's equal to minus the mixed second derivative with respect to parameter q and to the perturbation p. So this notation is like we have the second derivative taken first in the direction of delta q, here and here, and the second derivative is taken here in the direction s, where s is the derivative of the optimal point, and here the second derivative is taken in direction p bar, which is the perturbation of experimental data. So I consider a perturbation in a special direction, and I see what happens in the space of the parameters. So this is the sensitivity of the optimal point. Q hat is the solution of the parameter optimization problem. So it is the argmin of the reduced functional. So we have the first order optimized condition, this is the derivative in direction delta q. Thus, this first order condition define in an implicit way an implicit function. The optimal point is dependent on the perturbation of the data. So we differentiate the first order condition, and we get exactly what I've shown in the previous slide, where s, the direction in the parameter space, is the derivative of the optimal point taken at the point p0, so taken for given data. I need the data for solve the least square, taken in direction p bar. So a special direction in perturbation of the data. So s is the derivative of the optimal point q hat with respect to perturbation of the data z in direction p bar. Q hat is a local minimum. This was the assumption. That means the Sn is positive definite, and this problem has a solution. To simplify the notation, I write this sensitivity equation using this the notation. The Hessian is now H, and G is the Jacobian of reduced observation operator. So I have the Hs is equal G star, and then I'm using weighting matrix, because we use actually in the space of in the data space, we use weighted norm, and the weight is the inverse of the covariance. So we are actually considering the effect of Rathening of the covariance matrix. So the perturbation in parameter S is given by this guy, which is an operator which goes from the data to the parameter. And if I consider this Rathening property of CD, I just split CD in the product of square root. I consider a scaled perturbation P double bar, which has CD, square root of CD, the inverse of CD, times the perturbation we are considering now. That means P double bar are random values with covariance E. So I have normalized the perturbation in the data, and I get the inverse parameter to output operator. So G plus, considering also this scaling, is the inverse of the parameter to output. So it is like the output to parameter operator. If this operator is bounded, which is true for a finite element, for a finite number of parameters, and using regularization, then a spectral decomposition offers an appropriate tool to investigate the stability issues. So I consider a spectral decomposition of this operator G plus using singular values, and I say that the perturbation in the parameter is now given by like composition of several perturbations, which are given by the perturbation in the data, normalized, projected in the singular vector, in the direction of the singular vectors. And we see that this composition, of course, is scaled by sigma I, the singular the singular values, says sigma I, says which are the directional perturbation in the data which are the most perturbative for the optimal point. So of course here it's clear that there is an equivalence between the singular value of this operator and the eigenvalue of the covariance matrix, just using the definition of covariance matrix, which is the expectation of the variation in the parameters. So we see that actually the covariance matrix is this operator, and the power, the singular value to the power of 2 are equal to the eigenvalue of the covariance matrix. So now I can set the optimal experimental design in this setting, saying that OAD is the minimization of a functional of this matrix, which is a diagonal matrix where I have the singular values of this operator, constrained with my PDE and the sensitivity I need to define this operator, because we have the Jacobian of the observation operator here. I define some design variable and a functional, which can be, for example, the trace of the covariance, or like the sum of the square of the singular values, which is equivalent. And I consider not this formulation, but the reduced one. To consider the reduced one, I have to consider here for the solution a solution operator. So I say I can solve my PDE. I consider a solution operator for each sensitivity, so I can solve all the sensitivities. And I consider a functional phi, not of sigma, but of sigma hat. And sigma hat is now a functional which is reduced to the design variable space. And here I have a constraint. The design variable has to be in an admissible set of design. So a practical definition of an admissible set is the box constraint of the design. Not always it's not the only one, of course, depending on the problem. So I'm considering this one first. So I have the reduced box constraint optimal experimental design, which is minimization of a functional of the reduced covariance. with this box constraint. So the first order optimality condition is defined by not only the gradient equals to 0, but the gradient plus a Lagrange multiplier mu is equal to 0, and the Lagrange multiplier is defined this way. It's the maximum between 0 and mu plus a scaled distance to the bound plus the minimum between 0 and mu plus the scaled distance to this one. There are a lot of publications on these methods. I just cite a book from Ethan Kunig because you find here a derivation, and also showing it shows that this method is equivalent to a non-smooth, a semi-smooth Newton. I implement this in a so-called primal dual active set strategy. So this is like a active set type Newton type algorithm. So here we have a cycle where we have to solve, in each cycle we have to solve a linearized problem, exactly like in Newton. For doing this, we have to solve the state equation, and as we have to do with the covariance matrix, of course we have to do with sensitivity, so we have to solve the sensitivity or an adjoint problem. If you use a sensitivity, you solve so much linear equation as much as the parameter are. If with a joint approach, you just solve one of these problem. You calculate the Hessian and the gradient of the covariance, Hessian and gradient of the functional, like the trace. You update the active set, so you decide if you are on the upper bound and lower bound, and you cast everything in this linear. So we have here, you have the Hessian of this functional, and here we have an update of the Lagrange multiplier saying if you are close or not to the boundary. So as an example, I take again diffusion transport reaction. So as parameter, I want to find the diffusion coefficient, and the transport is a vector with two components. I consider 2D problems, and I want to identify only one component of the transport, beta 1. This is the variational formulation, and I consider a design. Also, as design, I consider the control on the boundary. So I say that I set a Dirichlet value on gamma, which is a subset of the boundary. And I consider also 4 positions. So I have a domain 2D, 4 position has to be found in a free way, and eta is a boundary control. I discretize this by finite element method, and here you see the control, eta. The other design parameter pi are of course in the covariance, because I'm considering here, I have not written here, but I'm considering point measurements. So I consider 4 point for the measurements. I have the constraint that pi has to be in the inner part of the domain, and I'm considering a square, so this is a box constraint, and this is also a box constraint for the control. And the solution is this one. So we have Dirichlet 0, 0, 0, and this is the control. Only the left side is the control. So this is a snapshot of the solution. It's stationary. I don't consider here time-dependent problem. The control, by control equal to 0, I have here Dirichlet on the boundary. This is a solution. These are the derivative, the sensitivity with respect to the 2 parameter mu and beta 1, and this is the derivative with respect to the control. And these are second derivative. The derivative, the sensitivity derived by the control parameter, which is eta here. And if I go to eta equal to 1, we see what happens. The solution from here goes to here, and the sensitivity from here having 1 spot and here 2 spots is going on the other direction, 2 spots for mu and 1 spot for this one. Of course, the derivative with respect to control remain the same as you see here, because the control is linear. So actually also in the Hessian of the covariance of I don't consider the second derivative, which are 0. The optimal design is if I consider 4 position, I consider 8 variables, because each position has 2 coordinates. So I have 8 variables and 1 control. I have 9 like design variables, and this is the optimal solution. The upper bound is active. So it's better to have a control which is going with a Dirichlet, with a higher value of Dirichlet, and the optimal position, as you see here, has converged in a design where I have two support points. This one, which is the same of this and the same of this, P1, P2, and P4 is the same, and P3 is a different one. So I have like two support, and the weight is like 3/4 in one point and 1/4 in the other point. Here there are some issues about the convergence of the Newton algorithm, considering the discretization problem and so on. I'm using finite elements, so I can discretize the state using quadratic function, linear function, and so on. You see that actually using quadratic function, the Newton or this active set strategy converts a bit faster than by Q1 for a state equals to 0. And if I consider this other state equal to 1, actually we have the much faster convergence for Q2. So this result will be available if this paper will be accepted by Simon optimization. And just very few overview of two cases where I'm using optimal experimental design. So I'm working on a project of fuel cells. There is a collaboration with Francesco Ciucci, who is here in the audience, and he will show a poster showing how we have published this, how it's possible to find in impedance spectroscopy the optimal frequencies to get several parameters in the fuel cells. And I'm also working in fuel cell with a group in Karlsruhe from a group of Professor Universität. They give us, make a 3D reconstruction of the fuel cells. We made a reconstruction by finite element, which is a 3D nonlinear stationary problem. And we solved this, the electrochemistry inside this microstructure. Here there are some publications, and I'm solving this by a software that I developed based on the finite element library DEAL2, which was developed also in Heidelberg. And now it's going on to be developed in Texas A&M. The OED problem will be set in this setting. We have to define which are the design variable. One is the temperature, the other one can be a partial pressure, and use the partial pressure is boundary condition for me. So that's why this was the motivation to have actually to start with this control on the boundary. I thank Francesco Ciucci for the collaboration. He is now in Heidelberg and is going to go to Hong Kong. Jochen Jost from Karlsruhe, and of course the DFG project that is supporting me, and you for the attention.
Thank you very much indeed. Any questions?
Well, I must admit, I have been lost in details. Well, too much functional analysis as for one such talk. But anyway, the relations of the information matrix with the Hessian of the least squares criterion are well known, and this was used by Kunish, by many researchers. There is a strong group in Moscow, researchers who work in the area of data assimilation. So this stuff is widely used by them. So I refer you to these works because they use a lot of parameters. So you have only 2 parameters, and they use try to find designs for problems where the number of parameters is really very high. And my question regards the novelty of what you have presented, because well, it's not clear for me. One novelty seems to me that this abstract formulation, you have weak forms of PDE, so this may be something new. But in the results, you showed us that, well, the points you select are found in one place. So we have clusterization of support points. So this phenomenon is widely known in experimental design as for spatial experiments. So I wrote much about this in my book.
I know. I've read the book.
Can you recapitulate the novelties of what you said?
First of all, I was glad that this algorithm is going to a solution that is well known. Actually, we have two parameters and we have two support points, and we are dividing like three measurements in one support point, one measure in the other one. I was expecting exactly this one. So I'm using here a well-known, let's say, problem to test the algorithm. So the first thing is the new thing is to have, let's say, derive this algorithm, especially for this kind of problems. And as you see, I could just considering this clustering and this point measurement, I can consider convergence issues and quality of the mesh, which is a very important question for PDE, for scientists. So people that PDE, I mean people from the community of optimization with PDE using finite element method. So for them it's very important the discretization. So to understand which is the influence on the discretization on the solution, which is the influence on the algorithm, which is the best discretization, and so on. So my idea is actually to go on this field, which is my field, finite element with PDE and optimization for this. OAD is only an application. Very nice application because it links the theory of parametric optimization, as we've seen, optimal control, and a lot of applications. So I see this very, very, very challenging and very interesting. The new thing, actually, there is nothing new. It's only that is written in a way, in a rigorous way, that can be understandable by the community working and using finite element method. That means working on this variational formulation. I had the problem starting with my PhD that there was no clear setting for the people coming from my side to understand how to write the optimal experimental design in our case without saying, okay, we take the Fisher information matrix. We know that is related to the Hessian. This is actually, you can find even in the older book of Atkinson, that is 75 book. So it's exactly, it is clear how it is, but I've never seen the rigorous formalization for this kind of problem. So for me, this actually is important for have a link to bring actually all this knowledge to a community which is not aware that a lot of things has been done in another way, written in another way. So actually, the actual contribution is actually to use this algorithm from this other community to this other community, because I think these are not algorithms that you are using, and try to write this problem in a notation in a setting where they. So it's the meeting of these two things. So I think it's enough for starting.
Okay.
Excellent, thank you very much.
Yes. So I missed, of course, many D's. You were doing D-optimality?
This was A optimality.
Oh, okay, in the question, yes, okay.
Yeah, but actually, the functionality doesn't matter here.
But if you did D-optimality, your weights would be a half, is that right?
Ah, okay, it could be.
Must be.
Must be. I'm not actually from the theory of.
Well, must not be. Must be.
No.
No. Good, okay, that's fine. There's something for us all to discuss.
In any case, this is a local solution, so it could be that there is a global solution which has different weights.
Henry's first.
Well, I mean, I work a lot with engineers, and it's commonplace to obtain sensitivities using the adjoint method or some clever variation method. That's usually done by the engineers. That's actually, most people know that there are now 4 uses of sensitivity. One is straight, old-fashioned sensitivity analysis. The second is identification, which is, everybody knows that. The third is optimization, because you need the gradients to do the optimizing. And the fourth is design, which uses identification as a kind of as the first step. So these 4 uses are really well known, and now in communities where statisticians work close to engineers. So I'm sure the elegance of what you did was clear, but this is not some new mantra that's kind of, there's already strong communication at least these four issues, maybe other issues I haven't thought of, but that's the big four. That's now done.
I take the suggestion and I take away the new on the title and I say a perspective, not a new perspective. You're right. It was more, yeah.
And last question.
Yeah, could you elaborate a little bit on numerical
Sorry?
discretization you had and
The arrow, you mean?
yeah, and if you used an adaptivity and
Not yet. I mean, this is the goal actually. We see already here that there is difference between using Q2 and Q1. Different a bit different solution. It depends on the age, of course on.
So could we see the mesh and maybe see a residual of sorts? A residual, like you do in energy-based residual.
No, I've still not done this.
Okay.
There is no error analysis here in fine.
Okay, but what
there
was
is
the
no
mesh
error
like?
analysis.
What was the mesh like?
Maybe we can
Yeah,
this one,
okay.
take this as
All right.
time.
Maybe I just make one advertisement. I mean, just to remember that we are organizing the Hanoi conference in 2012, March 2012, Hanoi. So this is the mini symposium, and then I would like to discuss later with maybe with some participants here on the possibility to organize a website where we can collect information coming from different fields of optimal parameter design, like publications and references, books, and so on. I have already organized a platform, and maybe we can discuss later here in the coffee pause. Okay,
Thank you very much.